Okay, so first of all, a couple of things of housekeeping. The title is Roadmap for Stellar Mass Black Holes. People at the Stellar Mass Black Holes workshop kind of laughed at me when I proposed this as a title, because this is the topic of a many month-long workshop, and we are generally struggling to combine all of this into a coherent story over multiple months, so how dare I try to do it in 45 minutes. That does mean that I will oversimplify, and I'm directing this almost exclusively to the people who are not from the Stellar Mass Black Hole workshop. So people who are, feel free to go and enjoy the weather outside. You'll be bored for the next 45 minutes. People who aren't, you're very much invited to interrupt me at any time, ask me any questions, etc. One request is people from my own workshop, please, even if you disagree with something or if you have some caveats, etc., please hold those thoughts until the end or subsequent conversations, because otherwise we'll never get anywhere. The second thing is just to say what I actually mean by stellar mass black holes. So astronomers find it rather awkward to measure the masses of objects in grams or kilograms because the sun's mass is about 2 times 10 to the 30th kilograms, and that's a bit awkward to write down. So instead it's easier to measure the masses of stars in the mass of the sun. It's the star we know best, so it's a good reference point. And so by stellar mass black holes, I mean things that are, let's say, between, roughly speaking, 2 and 100 solar masses. It's not exact numbers. The only reason I write down 2 is that things below 2 solar masses are, compact objects below 2 solar masses are typically neutron stars, so probably there aren't sub-2 solar mass black holes, at least of astrophysical origin. Some people have suggested there could be things called primordial black holes from early universe perturbations collapsing on themselves, etc. I will not talk about that. I will just talk about the astrophysical black holes that come from the collapse of massive stars.
But black holes below this range, I mean, below 2 solar masses, is it populated or?
Astrophysically, we do not know of any. And according to astrophysical models, we do not expect them to form through normal stellar evolution processes. People have conjectured, for example, that maybe even some of the dark matter mass in the universe could be due to stellar mass black holes, or sorry, not substellar mass black holes, very low mass black holes, and there are some regions where that has been excluded quite convincingly through a variety of different observations. There are some other regions where one could conceivably still have black holes with very low masses, and they are quite difficult to observe and constrain. So we cannot completely rule them out, but I'm not going to be talking about them. So maybe actually we should start with observations. So how do we even measure black holes with these kinds of masses? Well, a black hole on its own is rather difficult to observe because by definition it emits no light. Nothing escapes from the event horizon. So in general there are a few different ways that people have been observing black holes over the last 50 years or so. I'll actually go in a roughly chronological order. So the first one is accretion. So this means that there is some kind of gas coming onto a black hole, perhaps forming a accretion disk around the black hole, and so the picture is something like this. Here's my black hole, here's a disk around it from matter. As this disk is accreting onto the black hole, it gets heated to very high temperatures, and you're seeing radiation from this disk. Now, one wonderful thing about gravity is that it's actually a really useful astrophysical energy source, even though maybe we normally think that there are other processes in the universe that are other forces that are much stronger than gravity. In astrophysics, gravity does turn out to be actually one of the most efficient ways we can think of at converting mass into energy, right? If I think about, for example, even something like nuclear fusion, I get less than 1% of mc squared worth of energy per unit mass, whereas from gravity, it's possible to get tens of percent of mc squared. If I think about an accretion disk around a massive black hole, and for example, I think about what is the gravitational orbital energy at the inner edge of the disk, and let's say the inner edge of the disk around a non-spinning Schwarzschild black hole is going to be the radius of the innermost stable circular orbit is something like 6 gm over c squared, right? So if I ask what is the orbital energy there, and I pretend that I am going to do this in a purely Newtonian way, so it's going to be orbital energy at the ISCO. Okay, the orbital energy in general is gm over twice the separation, so in this case it's twice our ISCO. This is specific orbital energy per unit mass, and so this ends up being something like 0.1 of mc squared, so little m, or just 0.1 c squared since I'm doing it per unit mass, right? So I can get 10% of energy out from accretion, right? That's quite efficient, and so if this energy is coming out as luminosity, these things are going to be quite bright. And typically, these are being observed as X-ray binaries, because, as I said, the inner edge of the disk is hot, so the energy comes out in X-rays. And there are a variety of these X-ray binaries. There are low-mass X-ray binaries. There are high-mass X-ray binaries. They primarily differ by what is actually driving the accretion. Typically, the interstellar medium doesn't have a whole lot of gas in it. The densities are too low, so you're not going to get a bright source. You really want something that's donating mass to the black hole at a high rate. And so the way you do that is by putting another star nearby. And then one of two things can happen. Either this other star is actually being gradually tidally disrupted. So the tides being raised in it by the tidal gravity of the black hole are enough to pull off the outer layers of the star and transfer them to the black hole. People call this Roche lobe overflow, but it basically is just saying that the tides are strong enough that you're getting mass off of the black hole. These are low mass X-ray binaries, and they're feeding the black hole in just through mass getting ripped off. There is another version which are called high mass X-ray binaries. They're typically wind-fed systems, so that means that the massive stars are losing a significant amount of mass in winds, and some of those winds are being captured by the black hole as they're leaving the star, and again, you end up accreting onto the black hole. So I listed them first because these things have been known for about 50 years, maybe even a bit more. Cygnus X1 is perhaps one of the most famous ones. It was the subject of a bet between Stephen Hawking and Kip Thorne about whether or not this was really a black hole. We're now very, very certain that it is. So this thing definitely exists. There are a few tens of these systems known by now in general, containing black holes. There are a lot more X-ray binaries and X-ray binary candidates, but it's actually not trivial to determine which of them are black holes and which aren't. And what can we typically measure? So the observables, maybe I should use a different color. So the observables include things like mass, although mass of the black hole and sometimes mass of the companion as well. So black hole and companion. With a caveat, the masses are not always completely unambiguous because, for example, in some cases you have a degeneracy between the inclination of the binary's orbit relative to the line of sight and the mass of the black hole, but you at least have a way of measuring some kind of a mass function from these kinds of observations. You get some idea of orbital properties. So typically, okay, if you see a binary, you can at the very least measure the period of the binary, but sometimes you also get some of the other properties as well. Most of these systems are going to be fairly circular because of their mass transferring or close to mass transferring that often tends to circularize the binary either through some combination of mass transfer or just tides. Sometimes you get some kind of a systemic velocity, so the total velocity of the system. Not entirely trivial because very often we don't get to see the full, all 6 components of in the phase space, the position and velocity. So for example, unless you get a very good spectrum of the star. You might not know how rapidly the system is moving along the line of sight between you and the observer. Another challenge is that even when you do measure systemic velocities, because these tend to be quite old systems very often, at least low mass extra binaries certainly are, they can live in that stage for hundreds of millions of years, maybe billions of years. That means that these things have spent a lot of time moving around in the galactic potential, and so their current velocity may not have very much to do with their birth velocity, but at least you have some idea in many cases of systemic velocities. Sometimes you might get to have some information about the companion surface abundance. So what is actually sitting there in terms of the chemical composition. By chemical composition, I mean how much helium, how much carbon, how much oxygen, how much iron there is on the companion. And that can be relevant because maybe, as we'll discuss in a moment, it tells you something about the evolutionary history of this system. And you might, what else can you get? You can, well, this is kind of a big question mark, whether you can measure the spin of the black hole. So by the spin, I just mean the rate of rotation of the black hole. And I'm going to use for spin, I will talk about spin in terms of this parameter chi, which is a dimensionless parameter sitting between 0 and 1. And chi is basically the angular momentum in units of mass squared with enough factors of g and c to make this a dimensionless quantity. So 0 means non-spinning Schwarzschild black hole, 1 means maximally spinning Kerr black hole. There are measurements of spin, but this is where the word measurement, we should interpret very carefully. Unfortunately, in astrophysics, we often struggle to measure things directly, and even when we say we've measured something, what we really mean is we fit some complicated model to our data and try to infer something from the model. And of course, if that model is not perfect, if it has some systematics, then we get systematic uncertainties in the inferred measurement as well. And I'm not going to belabor the point too much, but just to give you an example, spin in particular here is a good example of this, right? You might say, well, how do you try to measure the spin? Well, maybe one way to do it, and there are multiple ways of doing it, but one way to do it is to look at the continuum of the flux from the accretion disk, and, well, you generally expect the inner layers to be, as I said, hotter than the outer layers, so you might say, well, maybe I could figure out from the overall spectral energy distribution, I can figure out how close in the inner layer is, right? How close in is the innermost stable circular orbit? Well, the location, according to general relativity, of the radius of the innermost stable circular orbit depends on the black hole spin. It's 6 gm/c squared for a non-spinning black hole, but for a prograde orbit around a maximally spinning Kerr black hole, it would be just 1 gm/c squared. So the innermost stable circular orbit moves in. So maybe that means that you should have a greater contribution of hot things in your spectrum, and from that you can figure out what the spin is, right? But then, if you think about it, for example, you might say, well, but these things are not necessarily moving, the disk is not in a perfectly Keplerian orbit. It would be if there was no coupling in the disk, if there was no viscosity in the disk, etc. But we know that there is viscosity in the disk, otherwise the disk would never spiral in. You have to transport angular momentum outward in order to allow the disk to spiral in, so we know that there is viscosity and there's coupling. And so does it mean that the innermost edge is actually at the innermost stable circular orbit, or could it be shifted relative to that, right? So this is the kind of model systematics that you have to worry about, and that's why I'm putting in some question marks about the spin measurements. Okay.
Can I ask you?
Please.
Are these systems tidally locked? Can we even tell if they are? Or?
In some cases we can. So there is a, so for example, I mentioned sigma 6-1 earlier. So in sigma 6-1, the rotation rate of the companion is equal to the orbit, the rotation period of the optical companion is equal to the period of the orbit to an accuracy of a few percent, meaning within measurement uncertainties, yes, it's absolutely tidally locked. Yeah. Okay.
Before you go
oh, please.
All these are in the Milky Way, right?
Some of the X-ray binaries are outside of the Milky Way, so even some of the, for example, high mass X-ray binaries, there are they exist in the Magellanic Clouds. They exist in M33. M33X7 is an example of a high mass X-ray binary. Yeah, yeah, relatively close by. Absolutely.
And how many, when you're talking about extra, what's the order of magnitude?
So order of magnitude of things that I would say we are very confident are black holes, a few dozen. Yes. Overall total number of let's say, X-ray point sources that are likely to be X-ray binaries of some description, much larger, but not all of them are necessarily containing black holes. In fact, most are not.
Since you started off talking about this mass range, did you give a mass range for these X-ray binaries, or is that later in the talk?
So these ones range typically from about 4 solar masses, give or take, to about, I would say, 20-ish solar masses. So, for example, Cygnus X1 is about 22 solar masses. And then it's actually an interesting question why they don't go higher. We'll talk about that in a moment when we talk about the coherent picture. Because, but one of the possibilities is that, for example, as was pointed out earlier, most of these sources are nearby, meaning that they're in the relatively high metallicity universe. So, meaning that they live in places where stellar winds are strong. And then when stellar winds are strong, even if you start out with a very massive star, it's hard to make a very heavy black hole out of it. So that could be one of the possibilities.
I heard once that the shape of iron lines was a way of measuring rotation. Is that still?
Yes, that's one of the other options. So there's, in addition to continuum flux, there's the iron K-alpha line reflection, and also possibly quasi-periodic oscillations. So there are a few different ways of doing it. They all have issues. They all have possible systematics. And in at least some cases, when there are a few systems where there are measurements available from more than one technique, and they don't always agree. And by not always agreeing, I mean that sometimes they disagree by far too many sigma to make you comfortable that things are really self-consistent. Okay, so that's okay. We talked about accretion. Okay, maybe not quite going in order, but it just makes sense to talk about this next. Is detached systems. So again, we have a binary, but now we have a black hole sitting here, and we have just a normal star sitting here and orbiting, of course, around the common center of mass, even though I've drawn the orbit as if it's around the black hole. There are a few different, again, ways you can actually tell that there is a black hole there, right? So one option is you just see the star astrometrically moving around. So Gaia is great for that. And one of the organizers of this workshop, there's Karim, is an expert on finding black holes in this way with Gaia, and has found, well, at least 3 of them that he is very confident about in this way. So the star is physically moving, and you can tell that there is therefore another heavy object that must be orbiting around. That object is very dim. You know you would have seen it if it was any kind of a normal star, and so the only solution is it's a black hole. There are a few other variants in this. So sometimes you can, if you get a good spectrum of a star, instead you can do radial velocity measurements, so you can tell again that the thing is moving, but not by physically watching it move across the sky, but instead by the fact that if this thing is on a in a periodic way, it's being Doppler shifted, right? So the thing is bluer because it's moving towards you, then it's redder because it's moving away from you, etc. And this is happening in a periodic way. Then you can be pretty sure it's orbiting around something. Again, you see nothing for it to orbit around, and so it tells you that it must be a compact object. And if you can figure out what the mass is, and the mass is heavier than a couple of solar masses, you conclude it's a black hole. Another way is that if the binary is quite close, but maybe not yet close enough to actually transfer mass, you might see what are called ellipsoidal variations. Basically, it has to do with the fact that your star is actually being distorted, and so as the star is moving around in the orbit, so the star is not a sphere anymore. It looks like kind of a teardrop shape facing towards its companion, towards the black hole. But now, as this thing is moving around in the orbit, right, you're seeing different aspects of the star, right? So here you see it, sideways in profile, and here you see the the back side of it, and here you see it sideways again, right? And you can imagine that if you carefully model what the star is going to look like, it's going to have the apparent sort of spectral energy distribution, for example, will change depending on which side of the star you're looking at, right? And that's the ellipsoidal variation approach. So this is this way of measuring black holes is relatively recent. It's really only the last few years that we've been getting good observations, thanks to a variety of new instruments that have come online. But again, at this point, we're talking about, well, at least a handful of very well measured sources and more very appealing candidates. Third one are gravitational waves. This, of course, started in 2015, so we've just celebrated the 10th anniversary of the first gravitational wave detection, the 150914, so 14th of September of 2015 was the first binary black hole merger observing gravitational waves. It's worth saying that here we're really looking at the very last few cycles in the merger of two compact objects. And by the way, these ones, in principle, the vast majority of them are indeed black hole binaries, but there are a couple of neutron star black hole binaries as well that have been observed in gravitational waves. A few of these, about 200 of these at this stage. Because you're only observing the last few cycles, that means that what do you get? Well, you get the masses, although again, you don't necessarily get both component masses perfectly. You typically get very well at lower masses. You get something called the chirp mass, which is, so the chirp mass is the thing which determines how the in-spiral evolves over time, how rapidly the frequency of the in-spiral changes. The chirp mass is just defined as the mass of the components to the 3/5 power divided by the total mass, the sum of the masses, to the 1/5 power. And that's well measured at low masses. At higher masses, you actually get a reasonably good estimate of the total mass, but not so good an estimate of the chirp mass. You can measure something about spins. When I say something, I mean that there are particular spin combinations that you get a reasonably good handle on. So, for example, something called an effective spin, which is basically the mass-weighted component of the spin along the direction of the orbital angular momentum, right? So, if you want me to write down a definition, it looks something like this. Chi effective is chi1, the dimensional spin vector for the first black hole times m1, mass 1, chi1 dotted into L hat, where L hat is the orbital angular momentum vector. Yes, please.
I know what's the spin of the electron, but like what's the spin of the black hole?
Yeah, so the spin of the black hole is just a statement about its angular momentum, right? So it just says how rapidly is it rotating, right? So if I think about the total angular momentum of the black hole, and it's convenient to get a dimensionless number to write it down in units of mass squared, then this tells me the spin of the black hole, and there's a maximum value allowed, which is 1. 0 is a non-spinning black hole. Yeah. Great questions. Yes, please.
Isn't there a range of masses where you get a significant number of cycles of the in-spiral still? You said few, but...
You're exactly right. So the lower mass things are, the more cycles you get, because basically the mass sets the frequency. So if I want to, for example, think about the frequency of gravitational waves from the vicinity of the innermost stable circular orbit, for example, the answer turns out to be the gravitational wave frequency disco is about 4 kilohertz divided by the total mass in units of solar masses. So that means that now the LIGO instrument is most sensitive at about 100 hertz, right? So if I start out with sufficiently low masses, right, I see the entire signal sweep through the LIGO band. But if I start out with something where the total mass, for example, is 100 solar masses, right, then the maximum frequency I can reach from the in-spiral is only 40 hertz, right? And that's actually below the really sensitive band of LIGO. So I might only get the last cycle or two in that case, and then I do get something called the ring down. So the ring down is sort of this quasi-normal ringing when after the two black holes have already merged, have made one black hole. That black hole is a kind of bumpy black hole. It's a perturbed black hole because astrophysical black holes, we think should ultimately be described by the Kerr metric, which means that they subject to some conditions. But the Kerr metric basically says that only the mass and the spin are important, and all the higher order multiple moments are completely determined by mass and spin. Whereas initially, right, okay, you just plump these two blobs together, right, and so you might imagine that now it has bumps in it, right, and so the space-time sort of doesn't have this clean picture, and this quasi-normal ring down is basically a way of getting rid of some of these higher order multiple moments in the space-time. And that happens at a higher frequency. That's maybe I should replace this 4 by 10 or so, but so then we're sensitive to the ring down, but the ring down really only contains information about the mass because it's really ringing at a fixed frequency. It contains just information about the mass, and also the quality factor of the ring down tells you something about the final remnant spin. The higher the final remnant spin, the more cycles it takes before you decay by a factor of 2 in the ring down amplitude, right? So ring down just contains 2 bits of information, basically, and even if you can extract them, and so then it becomes difficult to measure individual masses. You just have a total mass. So mass is something about spins. Obviously, we know basically next to nothing about directly at least about, certainly we don't know the environment because a lot of the times we can only localize things to huge error patches of tens of square degrees in the sky, so you have no idea what galaxy it came from and what the environment is. Whereas here, I didn't write down. We do know something sometimes about the environment. Maybe one thing we can measure here is a little bit about the eccentricity, although there's some debate about this. So the eccentricity of the orbit, because sometimes that can be retained even all the way down to merger. And maybe we can get some information about let's say, things like spin-orbit misalignment. So are the spins of the black holes aligned with the orbit? I didn't actually list here for my detached binaries what we can measure. So for detached binaries, again, we get the orbital properties. We get masses. We do know the environments. We know the abundances. On the other hand, we don't know anything about, for example, things like spins typically, because if the binary is wide enough, the spin of the black hole just doesn't have much of an impact on the properties of the orbit. So spins are not really constrained in that case. And the last thing I wanted to mention is microlensing. So the idea for microlensing is that you can actually see a single black hole. So you might say, how do I see a single black hole? Black holes don't emit light. Well, they don't, but they can distort light coming from other sources. So imagine you're looking at some background star, and there's a black hole that's completely disconnected from the star, that's coming between you, the observer. Here's me, the observer, looking at this, and suddenly I see that the star its appearance looks changed. In fact, if I look at the light curve, it's going to get a little bit brighter for a little while because the black hole passing between us is going to lens some of the light. So some of the light that would never reach my eye because it's going out, it would have gone right by me, it would have gone that way. It gets bent by this black hole sitting in front of me, and it now reaches my eye. So I get more photons hitting me, and so I think the star has gotten brighter, right? And it gets brighter for a little while. It gets brighter for something like the crossing time of the Einstein ring radius, and then it goes back to its previous luminosity, and so you say, okay, something has passed between me and the star. I don't know what the thing is, but I can estimate from the properties of the transient event how massive it should have been, and if I conclude that it should have had a mass of a few solar masses, I expect that if it was a normal star, I would have seen it, And if I don't see any other stars flying by, then I conclude that it was probably a black hole. The challenge here is that you typically, so what you can measure is the only things you're sensitive to are the mass of the black hole and the source lens relative velocity. And these two things are largely degenerate with each other. They're degenerate with each other because, as I said, it's the duration of the transit is the is the crossing time for the Einstein ring radius. So if you imagine the lens and the source are moving quickly relative to each other, you've reduced that time. If you imagine your black hole is a bit lighter, its Einstein radius is smaller, so you've also reduced that time. So those two things can have the same effect. And so we really are sensitive to a combination of these two things, except if we're lucky enough that we actually get really, really accurate astrometry for the star. So far it's happened once that this was possible. Hopefully it'll happen more in the future. In that case, you can try to break this degeneracy and separately measure the relative velocities and the mass of the black hole. Okay, so it took me half an hour to go through the observations. Now, what about the theory, right? Okay.
Before you get there,
Yes.
You mentioned at the beginning that your range was 2 to 100 solar masses. Where do you see the 2?
Oh, sorry, the 2 just came from, okay, so first of all, we actually, right, okay, so observationally, the lowest one that we've seen is actually in gravitational waves. There is a 2.6 or 2.7 solar mass compact object, which is probably a black hole, at least within standard equations of state. It's a little bit too massive for neutron stars to be comfortable as an explanation. There are a few systems that are actually in, for example, there's a system in this detached binary category which is sitting somewhere, maybe around 3 solar masses, but the mass measurement isn't very accurate on that one. So it could be 3, it could be 4, we're not entirely sure. To be honest, I wrote down 2 largely because that's kind of the maximum mass of a neutron star, and it just said, okay, things that are clearly more massive than neutron stars are, we're going to call them black holes. Whether it's exactly 2, it's probably not exactly 2. We actually do see 2 solar mass neutron stars. So maybe it starts at 2.2 or 2.3. Exactly where it starts is an interesting question, but that's a separate discussion. Yes, please.
So how often does microlensing happen, and how do you decide where to look to be able to obtain it?
Yeah, so it doesn't happen very often. You can just, there are quite a few. So first of all, these things are just seen in our own galaxy. The best place to look is probably the galactic bulge because you have lots of stars and relatively more black holes. So you just increase your chances relative to looking at some random star elsewhere. There are probably, there are multiple microlensing observations happening all the time, but the rate at which you're getting sort of decent black hole candidates so far has probably been order of magnitude 1 per year, I would say. That number is likely to increase as we have better instruments to go after these things. Yeah, and the number is just coming from the fact that we have something like 100 million black holes in our own galaxy. And you can just do a little calculation if you say, okay, this is what I expect for the velocity dispersion of black holes. How often will one come between a given star and us along the line of sight or close enough to the line of sight? And then you can, obviously you need to look at lots of stars, right? You don't follow just one star because then the chances are very low. So you use an instrument like OGLE, for instance, which is just staring almost constantly at lots and lots of stars in the direction of the galactic bulge, the center of the galaxy, and then that's how you get these kinds of observation rates. Please.
And when, kind of this balance of kind of matter and everything else there, this mass of black holes is it enters, or it...
So the astrophysical black holes probably don't contribute very much to dark matter, if that's what you're suggesting? No, sorry.
Overall, just I'm asking about the total balance of matter against, say, radiation or whatever, in the universe.
Right, okay, so...
Not specifically, not for dark matter, because I don't know, you are not counting black holes as dark matter, right?
Well, you could actually. I mean, and some people have suggested you could, right? But I'm saying that the astrophysical black holes aren't going to be a significant contribution to dark matter that way, because only stars that are sufficiently massive, which is a relatively large fraction, relatively small fraction of stars, actually make black holes, and so that means that the total mass locked up in black holes is a small fraction of the mass that's at any given time that's locked up in stars or that's available in gas, right? So they don't contribute very much that way. If you look at contribution to radiation, okay, gravitational waves, for example, probably are something like 1 part in 10 to the 15th of the closure energy density of the universe, if you look at the integrated energy density in gravitational waves, right? So it's not very, it's 10 to the minus 15, so it's not particularly significant. If you look at the total energy that's coming out of accretion onto black holes, this actually, for some things, is very important, right? So, for example, people have suggested that this could play a very big role in the reionization of the universe, for example, because this is one of the ways you can get hot, high energy photons that can ionize things out, right? But again, in terms of the overall energy balance, well, the universe is not radiation dominated at the present epoch anyway, so it's not that important, right? Yes, please.
I just have a silly question. So here, these are kind of different scenarios where black hole interacts with something and send you a signal that can measure, right?
Yes.
Do you have different models for each event? Because I'm trying to think of it, and one black hole can never send you a signal in different ways, right? So are you sure that the same? You're describing all these things in the same way? Do you know what I'm?
Yeah. So do we have a theoretically coherent story for how these things form? And indeed, the reason I spend so much of the time describing this basic picture is that it is important for trying to figure out, okay, what we can actually learn, right? The data is driving what we can actually hope to learn. So I probably won't be able to say very much about what we can actually hope to learn because I think I have 5 minutes left, but let me at least, maybe I'll go on this side, at least say the kinds of questions we're asking ourselves. So I sort of thought about, how I might be able to group them, and I would group them in the following way. So one question is black hole formation. How do we actually form black holes? So what are the progenitors? I think, when I first started as a PhD student, the very simple story I was told was that stars that are below 8 solar masses make white dwarfs, stars that are between about 8 and 20 solar masses, and you can quibble whether it should be 20 or 22 or whatever, but somewhere in that range make neutron stars. Stars that are more massive than 20 solar masses make black holes. Now, it's becoming increasingly clear the picture is not quite as simple, and there may be very different ranges of where things do and do not explode, and it may not be a simple monotonic function of mass, that heavy things make black holes and light things make neutron stars. Some people have conjectured that it has a lot to do with how dense the inner parts of the core are. So the compactness parameter, if things are very compact, they're hard to explode, and therefore compact things will make black holes, and low compactness things will explode and make neutron stars. And even that would not be completely monotonic as a function of mass, but other modelers find that actually if things have a very high compactness, then there's actually possibly also more energy coming out during the collapse, and so therefore you might, despite the high compactness, be able to unbind a lot of the material because it's a more energetic explosion, and because it's always a trade-off between trying to push out a shock that tries to unbind the material and gravity, which is trying to pull it in. And so who wins, I think, is still a bit of an open question, even from the perspective of people who do detailed supernova models. So progenitors are one question. The remnant masses are another question. Do we form black holes through complete collapse, where at some point everything that used to be part of the star goes into the black hole with no explosion? Or are there sometimes explosions where there isn't active supernova, but some of the mass manages to fall back on the proto-neutron star, enough mass to leave you with a black hole? There's at least some evidence that sometimes things really do experience complete implosions where there's no supernova and you just are left with a black hole. So I'll give you a couple of examples. We've actually heard at the conference last week about another observation, it's not the first one, of a disappearing star. So if you look at very massive evolved stars, you expect that, of course, some of them will go supernova, but if it's true that these complete collapses happen, then sometimes you should just look at a star and see that the star disappears, or almost disappears when it collapses into a black hole. And there are now a couple of examples of that apparently happening. There are other examples. For example, if we look at some detached binaries, I mentioned we can measure orbital properties. You can see, for instance, there's a system called VFTS 243, which has a black hole in a star. The binary is wide enough that tides should not have been important, and yet we see that there's almost no eccentricity in this binary, and we also see the binary has a very negligible systemic velocity relative to its local standard of rest, and that tells you there should not have been any mass loss or any natal kick, right? So no asymmetry in the explosion. So that's only consistent with a complete collapse story. Spins. Maybe we have some idea at least that things that are born with a lot of angular momentum, and then if they do experience complete collapse, it's sort of hard to imagine where the angular momentum would go, so presumably they keep the angular momentum of the progenitor. And if that's the right story, then there's a question of how can the black holes have a lot of angular momentum. If you, for example, were to believe some of these measurements here that do claim that in some of the high mass X-ray binaries you have a significant amount of spin, then the one possible way to explain that is that the progenitor must have been rapidly spinning, and maybe the way to do it, for example, is through tidal locking in a binary, because otherwise it's sort of difficult to avoid spinning down through mass lost in stellar winds. But again, an open question here. There is the question of black hole evolution. So here we primarily talk about things having to do with accretion, because it's actually kind of difficult for black holes to evolve in any other way, right? Unlike a star, which does all sorts of interesting things, a black hole is just born and accretes gas. Now, it actually has to accrete quite a bit of gas for things to be really interesting. So, for example, if you ask how much gas accretion does it take to change the spin of a non-spinning black hole from 0 to something like close to unity, you have to double the mass. And doubling the mass in a lot of these systems, as we understand it, is difficult, because if we believe that black holes have a limit to how fast they accrete, there's something called the Eddington limit, and it basically says that if you accrete too fast, the radiation pressure from the feedback from accretion starts pushing out on the accreting gas, and so you actually self-regulate the accretion speed. And at the Eddington limit, it takes something like 30 million years to double the mass of a black hole. But if we're talking about a system, for example, with a high mass companion, like a high mass X-ray binary, that companion star has a lifetime much less than 30 million years. And so you just don't have enough time, if you're really Eddington limited, to double the mass and therefore spin up the black hole to be nearly maximally spinning. In low mass X-ray binaries, again, there the problem is the companion is just, at least as we see it today, is often very low mass, so it doesn't have enough mass. Now some people, like Philip, for example, have suggested that maybe the low mass X-ray binaries used to be intermediate mass X-ray binaries, they had more mass in them, you donated a lot of the mass to the black hole, that may have spun up the black hole, and that's certainly a possibility to consider. And the third question is formation. And this is formation in particular of binaries, right? Okay, the single or apparently single black holes are easy in this sense, but how do we make these kinds of binaries, these kinds of binaries, these kinds of binaries, and what does the fact that they form in the first place tell us about stellar and binary evolution is, at least for me, one of the most exciting topics here. And there are all sorts of physics involved, it's not just about black hole physics, although that is certainly part of it, the things I already listed, such as black hole formation, but also things like mass transfer physics, things like stellar winds. And the hope is that it's the diversity of these kinds of observations. They're each telling us slightly different things about black holes. They're probing different ranges of black holes and different properties of systems. Some of these systems might not have been forming starting out as binaries. They might be starting out as triples, for example, because most massive stars are in binaries, but also most of them are in triples and higher multiplicity systems. Some of them may form dynamically in dense stellar environments, like globular clusters or nuclear clusters essentially of galaxies, through interactions already after the black holes have formed. Others might be born in even more exotic places, like disks around active galactic nuclei. And so the hope is that we could come up with some sort of a coherent story that puts together all of the observations and all of the observational constraints, and actually tells us something about not just about black holes themselves, but uses black holes as probes of other interesting astrophysics, such as mass transfer physics or dynamics in dense environments. But I think I'm at the end of time, so I will have to stop here. Thank you.
So, Kavli, it would be great if you could observe three objects, right? A black hole and two stars, or a binary black hole and one star. And any of those.
There have been systems observed, for example, triple systems, where you see a low mass X3 binary, for example, so a black hole, a star, and then another star orbiting around it. Karim is smiling because he is one of the people responsible. So yes, absolutely. And that's, I think that the database of such systems is rapidly growing.
What about two black holes and a star?
I am not aware of us having such a system yet, but I think it would be difficult to tell that there are actually two black holes in that case. There have been some...
I mean, you see nothing and a star going around, but not in our lips. That seems more interesting.
Yes, so it would have to be then you have to sort of play around with the mass ratios and the separation ratios, right? Because if the star is too close, the system is actually dynamically unstable, so it shouldn't survive for very long.
First of all, it would be in Gaia, whatever, a star going around, but not in a Kepler ellipse.
Yeah, and microlensing is actually another way of doing this. I mean, I agree it would be very exciting to see this, right? Because here, again, you might see an interesting behavior if you actually have a binary on the inside rather than a single object. It's just hard because of the separation scales. Yeah, Tom, please.
Lisa would be good at that.
Yeah, Lisa would
Yes.
tell us that for sure.
Yes. And people have also looked, not so much in stellar mass black holes, but in more massive black holes, right? People have looked to see if there's evidence for supermassive black hole binaries, for example, the centers of galaxies, and whether, again, a variety of channels for how you might infer that, for example, tidal disruption events are occasioned by the presence of a pair of black holes, supermassive black holes, rather than a single one.
Okay. Yeah, so are there models of, say, 100 solar mass black holes that don't involve mergers? Can stars just collapse at 100 solar mass?
So there is a range of masses where it's hard to make black holes from single stars because of something called pair instability supernova. So the idea is basically that if you have a very massive star, it gets very hot in the late stages of its evolution. It gets hot enough that you might naturally have the photons inside the star pair produce electron and positron pairs, and that means that you get yourself very close to the gamma equals 4/3 threshold of stability, and so you might actually have a runaway explosion, and in the models, due to people like Stan Woosley, nothing is left behind, right? The entire star explodes away. Now, exactly what the mass range is for that is still a question of some debate because we don't know all of the nuclear reaction rates perfectly, but it's indeed entirely possible that, let's say, between 50-ish and 130-ish solar masses, it may be very difficult to form single black holes without appealing to a merger somewhere along the line. It could be either a black hole merger or actually in some cases maybe even some stellar mergers could help you, because if you merge two stars together, but at the right point in their evolution, you might end up with a somewhat anomalous core mass to envelope mass ratio, and that might allow you, under certain circumstances, to create a more massive black hole than you would normally expect. But then there should be, again, in this picture, in the pair instability supernova picture, there should be, again, black holes from normal stellar evolution at masses above, let's say, 130 solar masses, because at some point there are other ways of absorbing the excess photons, and so you can form more massive black holes.
I wonder about the status of these primary black holes, because being ignorant, I'm not sure, but still, the existence of these heavy black holes, is it supportive for existence of primary black hole formation, or?
You mean primordial black holes?
Yeah.
Okay.
Yeah.
Now I'm going to speak to my personal preference, right? So I don't see at the moment from just the point of view of observations, I don't see an obvious reason to have to appeal to primordial black holes. Occam's razor tells me that there are enough uncertainties in the physics here that we should be able to explain things using just normal stellar evolution physics. I think it's pretty clear that in the tens of solar mass range, we certainly can form black holes through stellar evolution. There is no a priori reason why we shouldn't be able to do it at higher masses. In fact, again, there are some constraints about how many massive black holes, primordial massive black holes you can have. Let's say by massive I mean thousands of solar masses, because they should fly through star clusters often enough that they would disrupt star clusters. And the fact that we see those star clusters tells us that there isn't a large population of thousands of solar mass black holes just flying around the universe.
No, but I think it's also related to how many black holes we have, because if primordial black holes were there, then they could, be contributing to this, right? But I'm not sure what is the status, so that's why I'm asking.
Yes, well, no, you're right. We cannot rule out that they could contribute. I'm just saying that yes. So there's enough. Okay, if we're talking about, for example, if we're talking about X3 binaries or detached binaries, it's sort of difficult to see why you would have a primordial black hole with a star orbiting it, right? So these ones, I think we can be pretty confident they're coming from stellar evolution, right? Gravitational wave sources or microlensing, yes. I don't think we can rule out that some fraction of them come from primordial black holes. It's just a question of, Occam's razor. My personal Occam's razor says that we should explain them in the same way.
If you put it all together, all the observations and the theory, how much do you know about the total number, density, distribution of black holes in the galaxy?
Yeah, I think that we can be reasonably confident there are about 100 million order of magnitude black holes in our galaxy, stellar mass black holes. Yeah.
And that's with what uncertainty?
Factors of a few. Probably not too much more than that. I think the combination of how often we see these things in microlensing, how often we see them in binaries. Okay, maybe one or plus or minus a factor of 10, let's say, or sorry, divide or multiply by a factor of 10. Apologies. Yeah, plus or minus doesn't work.
You commented on this pair instability, large masses a minute ago. To what extent is that influenced by metallicity? Is it significantly different for low metallicity and high metallicity, or is it about the same?
The pair instability itself, if you talk about what core masses are going to give you things that are unstable to pair instability, not so much, but it does have a strong effect on which initial masses might put you in that regime. So, for example, at metallicities of the local universe, local galaxy, like solar metallicity, you might conceivably never have pair instability supernova, because even if you start out with a 200 solar mass progenitor star, it will lose so much mass during its stellar evolution that by the time it reaches the end of its life, it might only be able to give you a 20 solar mass compact object below the threshold of where you would expect to have pair instability supernova, right? And so Peninsula supernova, that's one of the arguments for why we don't see very many of them. It's a question of whether we see actually any of them, but that's a separate story. But one of the possible answers is that our local neighborhood doesn't go to metallicities low enough. Oh, I'm sorry, I should say, I keep on saying metallicity. I didn't actually define my terminology. I apologize. Astronomers, I used to joke when my daughter was very young that she would make a very good astronomer because she knew how to count 1, 2, and many. That's sort of what astronomers do. So to an astronomer, metallicity refers to the fraction of elements other than hydrogen and helium. The idea being that hydrogen and helium are formed through Big Bang nucleosynthesis, and everything else is a result of processes going on in stars. So that's why everything else is called a metal. But for our purposes, the important thing is that metals determine the strength of winds, the rate of mass loss of stars. The higher the metal content, the stronger the winds are. And so at high metallicity, it's difficult to form massive remnants. And that's the relevant part of metallicity for this question.
Okay, thank you very much again.
Thank you.